Once you have sequenced a genome, you need to figure out what parts of genomes are actually making genes. This computationally in the bioinformatics is called the gene prediction problem. So before that, actually, the sequence assembly, so you basically have you can put all your short reads into long reads. That's probably not going to cover today. But once you have that, you need to figure out what parts are expressed and what parts are not. And you can basically do this as a part of two different methods. You can try to do completely pure computer-based ab initio, basically figure out what is actually, how does the gene look like, and how can we identify the regions of the genome that looks like a gene. But you can also use it by comparing to already existing genomes. So you can identify similarity in the DNA sequences. The reason why this works is because the gene coding regions are much better conserved in evolution than the non-coding regions. Because the non-coding regions, there's no selective pressure to conserve them, or at least very weak selective pressures, so there are random mutations all happening all the time. While in the genes, many mutations are not accepted. So today, methods use a combination of these methods. But still, we should know that it's almost impossible to say exactly what genes exist in the genome. So this results in today that we actually don't know how many genes there are in the human genome. There are numbers that change all the time depending on exactly how you define the genes. And they're probably actually not the same number in all of us, because there are parts of the genome, parts that are expressed in some of us, and some parts that exist in some of us, and some are not in others. But anyway, when you have a genome project, you need to use these methods. So in the prokaryotes, it's actually it should be rather simple to find a gene, because basically the idea is if you find a long open reading frame without any stop codon, it's most likely a gene. Because as I said before, on average, every 21st codon, triplet codon, is a stop codon. So if you find 50, 60, 100, 200 codons without a stop codon, then it's very unlikely to happen by chance without being a gene there. So basically what you can do, you can take the genome, you search for all possible 6' reading frames, you calculate the vector features, check how long they are, you look for start codons and you find how long is it, and you find a stop codon. You know that you should have a Tata box or some other regions that are particular for the prokaryotic upstream region, etc. And you find a process set of prokaryotic genes. And then what you want to do is to search for these and see if these regions are conserved in other related genomes. However, in eukaryotes it's much more harder because there are short and long introns. So you need to find also intron and exons, splicing signals, and the exons are much shorter than many genes in prokaryotes. So can easily be mistaken by non-coding regions that don't have the stop codons in them. So, but you can make a model, you can make a computational model using something also called hidden marker models that we'll discuss later, and you can have programs that do that. So here after prokaryotic genomes, you see that the genes are often quite dense. There are very short areas between the genomes, and they can go both directions. So, and this is the result in the eukaryote.